afternoon and welcome to RCIScience's Science on Sunday, Strange Signals. I'm Kirsten Vanstone, a former RCIScience Executive Director. Hello to those of you that I know, and also a longtime member of our partner organization for this event, the Toronto Centre of the Royal Astronomical Society of Canada, or RASC. It has been more than a year since we gathered together at the McLeod Auditorium, and though the pandemic prevents us from being physically in that location, we still acknowledge that our usual meeting place is part of what has been for thousands of years, the traditional land of the Huron-Wendat, the Seneca, and most recently the Mississaugas of the Credit River. Today, our meeting place at the University of Toronto is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. As it happens, I am also on that land today where I live, but one sort of good consequence of the pandemic is that we now reach people from all across Canada and beyond. Wherever you are, you can research the Indigenous cultures that exist in your area using the useful and really interesting website, native-land.ca. Our speakers today are going to be discussing an astronomical mystery, fast radio bursts. Before we move on to that, though, I would like to take this opportunity to mention the passing of another astronomical sleuth who, using the big telescope at the David Dunlap Observatory in Richmond Hill, Ontario, uncovered the first observational evidence of the existence of black holes. His name was Professor Tom Bolton, and he was a fixture at the University of Toronto Astronomy and Astrophysics departments. Alternately terrifying and delighting his students, I should know I was one of them. I would urge you to read the obituary in last Saturday's Globe and Mail newspaper, written by Tom's former colleague, Professor John Percy. Professor Percy is a past president of RCIScience and also a winner of our Fleming Medal for Excellence in Science Communication. The obituary is evidence why, in it, you will find a compelling story, not just of Tom's contributions to science and his championing of light pollution abatement, partly to preserve the sky for local observatories, but also a very human story of the scientist himself and the social context that brought him to come and work in Canada. I mention this not just to mark the passing of an important astronomer, but also to note that nominations for the Fleming Medal are being accepted until March 15th. This medal recognizes excellence in science communication. So if you know a Canadian science communicator who has made a demonstrable impact on the public understanding of science, please nominate them. Send a letter explaining why you want to nominate them, preferably with at least 2 other letters in support of your nominee. This is an important award, and RCIScience wants to hear from you about who should receive it. Okay, on to today's program. I'm very excited to hear about fast radio bursts because I've heard a lot about them, but I actually don't know that much about them exactly. I still don't really understand what they are, which I'm pleased to say was also the case for most astronomers until quite recently. Our event will start with a short presentation followed by a fireside chat and then a moderated question and answer. So please do submit your questions. You can use the chat box if you're in YouTube or the comments if you are watching via Facebook. You can also send us a tweet at RCIScience or by email. You can send questions by email to information@rciscience.ca. And while I don't imagine that fast radio bursts are likely to stir up controversy and arguments, please do keep your comments polite and respectful. Moderators will be having a look at the chat box and comments and taking action if needed. So without further ado, it is my pleasure to introduce our moderator today. That is Nicole Montalaro. Hello, Nicole. Nicole is an amateur astronomer. She is an editor of the Journal of the Royal Astronomical Society of Canada, which is a long and venerable publication that I have many of on my shelf. And she is also a senior science reporter at CBC News, who's been very busy recently with all the stuff going on. In addition to that, she's the author of several books, including the 2021 Night Sky Almanac, a month-by-month guide to North America's skies from the Royal Astronomical Society of Canada. And I also happen to know that Nicole is a big fan of science fiction movies and TV shows. Taking us on this mysterious journey is Professor Keith Vanderlinde.
Hello.
Keith is an experimental cosmologist. Hi, Keith. How are you?
Good, thanks.
I'll launch into your bio here. An experimental cosmologist and long wavelength instrumentalist at the University of Toronto. He has spent the first decade of his career studying the oldest light in the universe, that is the cosmic microwave background, CMB, and that included spending 11 months in Antarctica operating the South Pole Telescope. We were just chatting about that before this started, and it's a fascinating story. Lately, his work has focused on cosmology with radio telescopes, which are undergoing something of a revolution thanks to the explosion of digital computing power. Keith and his team developed the custom supercomputer at the heart of the Canadian Hydrogen Intensity Mapping Experiment, otherwise known as Chime, which transformed it from a traditional telescope to one that can simultaneously look in 1,000 different directions at once and run a dozen distinct studies, from mapping the universe to unearthing fast radio bursts. Now, if that wasn't enough, he's now leading the digital system design on a telescope in South Africa and co-leading the upcoming CHORD telescope here in Canada. So I'd like to give Keith the floor now, who's going to give us a short presentation about FRBs and the Chime telescope and all the cool stuff going on in radio astronomy.
All right, thanks very much for that intro. Hopefully everyone can see my screen now. I'm talking today about strange signals, chime, and fast radio bursts. Before I can get into the fast radio burst portion of it, I do want to spend a minute on sort of my background and how I got to be here, and how it is that starting a couple of years ago, my work started getting reported, that of me and my colleagues, started getting reported in popular press with headlines like "Mysterious radio signals from deep space detected," picked up by a telescope in Canada. This is not the background that I come from. I'm a cosmologist. I study the universe on grand scales, and mysterious radio signals aren't typically something that I would think of as part of my wheelhouse. So to explain how I got here and to get into the fast radio burst portion of everything, I wanted to take a couple steps back and just sort of get everyone on the same page, start from the beginning, and start with just the basic concept of light. All the colors of the rainbow, right? From Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. But that isn't the entire rainbow. That's just the rainbow that we can see with our eyes. There's a whole lot of rainbow beyond that, many, many more colors of light. And if you sort of zoom out from that, you get the entire spectrum, starting with gamma rays at the extreme high end, through X-rays and UV light, through visible light, infrared, microwaves, and radio waves. And the real point that I want to make here is that these are all the same physical phenomenon. They're all just light. The only thing that makes optical light particularly special is that our eyes see it. So it's the one we're used to working in. And today I'm going to be talking more about radio waves at the extreme end, but it is still light. It's still fundamentally the same process. So you can look at the sky. This is just taking the entire astronomical sphere and unrolling it. This is what the visible sky looks like. Here's the Milky Way through the middle, all of the stars in our galaxy, and you can see dust belts and all sorts of things, the large and small Magellanic Clouds. That's the view of the sky in visible light. Just to be clear, when I say all I'm doing here is taking the overhead sky and flattening it out, like is shown here for this globe of the Earth. I'm not saying that the sky or the universe is an oval in any way. But you can look at the sky in all of these other wave bands, in all of these other colors of light. From gamma rays, if you look at it, you still see our galaxy running through it, but you see a lot of these extragalactic sources, which are crazy things like active galactic nuclei, superheated gas falling into black holes, and things like that. If you look down in infrared, you see mostly stars in our galaxy. Infrared's great for looking for stars or looking for things like exoplanets, where they're a little more visible against the background. I come at this from the lower end, though, microwaves and radio. Where I started was the microwave sky, and this is not a display error. This is a picture of the microwave sky. This actually is a picture that effectively won a Nobel Prize back in the 1960s. Because this is the oldest light in the universe. The whole sky, if you could see microwaves, glows all the time. And it's just filled with microwave light, left over from when the universe was really just a baby. And it's not just blank. Studying this gray blob isn't quite what my career was. If you turn up the contrast by about a factor of 1,000 on it, you can start to see more interesting things. You can, again, see our galaxy poking through. It does emit some microwave light. But there's all this other funny structure everywhere. And this is the stuff that I started my career in cosmology studying. I did it with an instrument called the South Pole Telescope, creatively named because it's the 10-meter South Pole Telescope, a 10-meter telescope located at the South Pole. This is a picture I took, beautiful aurora australis and a really impressive landscape. The downside is that to be there to run that sort of telescope, you have to hang out through the Antarctic winter. And it gets to be somewhat cold. The wind chill on a bad day gets below -100. The temperature typically sits at -70 or so. So operating telescopes in funny environments is sort of the name of the game now. And if you really want that clear view of the early universe, going to the South Pole is just one of those things you have to do. This is the sort of picture that you get out of the South Pole telescope. All of these diffuse sort of fuzzy clouds. This is showing just a little cutout of the sky. And it really is just a photo. It's the light that the universe gave off when it was only a tiny fraction of its present age, something like 0.003% of its current age, right? This is a baby picture of the universe. And it lets cosmologists study all of the strange physics that's going on in here, creating these funny cloud-shaped structures. And now that's a reasonably well understood aspect of cosmology. This cosmic microwave background has been heavily studied at length with a lot of different telescopes on the ground, in space, in easy to get to places and hard to get to places. And we understand what's going on reasonably well with that. It tells us about what the matter is doing in the universe, how much light there was relative to matter, how much dark matter there is, what dark energy is up to. All of the basic constituents of cosmology are sort of shown here. And this filamentary sort of gassy structure, if you run the clock forward, evolves into what we call the large-scale structure of the universe. This is a picture of a simulation of a very large volume of space. Right? This is 2.3 billion light years shown by this bar. And this filamentary stuff is really tracing out where all the mass is in the universe. And if you look at one of these pixels, you might be looking at half a dozen galaxies sitting in it. So this is really zoomed out, right? We're talking about hundreds of billions of stars in each one of these pixels. But on that sort of scale, the universe does form into this kind of spongy structure, which grows out of that structure you can see in the CMB. And nowadays, this is the structure that I'm studying. You look at the more nearby universe, the later evolved universe, and try to map out what this large-scale structure is doing. And this is something that cosmologists have been up to for a while. If you want to map the large-scale structure, you can go out and you can just measure where there are hundreds of thousands or millions of galaxies. You can take expensive optical telescopes and start putting down pinpoints everywhere you see a galaxy. And if you plot them all up, it looks something like this. And you can see that sort of spongy filamentary structure coming through here. But that gets really hard. We're at the origin here. People have done it in these wedges. This is one of the early ones from 2003 from the Sloan Digital Sky Survey. But as you get farther out, you can see it starts to peter out. And that's just because as things get farther away, their light is more spread out by the time it gets to us. It's more diffuse, and it's just hard to pick up enough light to be sure if there's one galaxy, two galaxies, or what's going on exactly. Everything gets too faint to really see. So if you want to map out this structure, you have to start coming up with other options. And the option that I and colleagues settled on is trying to use radio light. Rather than using the visible light from stars, essentially, you can look at these galaxies and you can look for radio that's emitted by the neutral hydrogen in them. Hydrogen is the most abundant element in the universe, something like 3/4 by mass of the universe's matter is in hydrogen. And neutral hydrogen naturally glows faintly in radio at a very specific color of radio light that it emits. And if you could look for that, there's so much hydrogen everywhere, you'd think you could see, well, a much larger volume of the universe. So you could use a radio telescope to try and map out this large-scale structure. Now, it turns out that's harder than you might expect. There are three basic problems. One is that the universe is largely ionized. So the hydrogen that's out there, the vast, vast, vast majority of it isn't neutral, which means it doesn't do this radio glow. The glow itself is produced, if you look into the atomic physics of it, by something that's a forbidden transition. It's a change between two states in an atom that can't actually happen. The laws of physics prevent it from happening. And the only way that you can get that light is through a really circuitous route that takes, on average, about 10 million years for a single atom of hydrogen to emit a single photon of radio light. So it's really, really rare. And thirdly, just like with looking at visible light from starlight, we're trying to look at very, very distant things. So at some level, we're trying to look for a signal from something that isn't there that can't happen and that's too far away to see anyway. So you might think this is a bad idea, but it turns out there are ways around it. If you can build a sufficiently sensitive telescope, you can. This might be the sort of measurement that you could make. And when I say sufficiently sensitive, I mean ridiculously sensitive. If you took the Arecibo telescope, which sadly was damaged to the point of decommissioning late last year, it would take decades on a telescope like that, that's 300 meters across, to make this sort of measurement. If you use, say, the Green Bank telescope, which is the largest steerable radio telescope, fully movable, it would take centuries. That's about 100 meters across. And neither of those sounds like the sort of thing that I want to get involved in early in a career and wait for generations on generations of cosmologists to do it. So you have to take a step back and think, okay, that might not work. What else could we do here? You think about it and go back to the basics. How does a telescope work? Well, a traditional refracting telescope, one with a lens, uses that lens to focus light down onto a detector. And you put a detector there, and then you can collect all the light across the whole lens. In a mirror, a reflecting telescope, it works the same way. You put a big mirror, it focuses all the light that hits it down to a point, you put a detector there, and you get all of that light. Great. Both of those are too expensive. We would need too big a mirror, too big a lens. It's not going to work. But we understand the physics of light really, really well. We don't need to use a mirror, actually. At radio wavelengths, at radio frequencies, this light is slow enough at some level that we can do all of this math ourselves. We can apply the physics. We can figure out how this would reflect and how it would focus down to a point. And instead of using a mirror to do that, we can just record all the signals of the radio light on the ground and then make a computer do it. We can program a computer to focus all that light in its memory. And instead of spending all our money on a huge mirror made of steel, we can spend all our money on a computer made of silicon. And it turns out the computers get cheaper and cheaper and cheaper every year and more powerful. And physically, this operation is still identical to using a traditional dish. Now, that's great because it turns out there's even more that you can do. Once we've got all of these detectors and we've recorded all of this radio light coming in, we don't just have to use it to look in one direction. We can add it up a different way. We can apply a different series of operations in the computer and have it look somewhere else. So if you have a big enough computer, you can make this look in lots of different directions at the same time. You just copy the data and reprocess it a different way. And that's incredibly powerful. Now, the downside is that this takes lots and lots and lots of detectors, and it takes a huge computer. Processing light is expensive. Thankfully, consumer technology solved both of those problems in the last decade or so. The first happy coincidence is that cell phones came into being. Cell phone users want cheap devices, strong signals, and cell phone amplifiers are really just kind of miracles that let you build these detectors for pennies on the dollar. Instead of not even pennies, instead of spending hundreds of thousands of dollars to build one detector, as would have been in the 90s, you spend dollars, which suddenly makes this more affordable. The second coincidence is that the processing that we need to do, all of that physics that we need to apply in the computer, is the same as projecting from a three-dimensional volume onto a two-dimensional surface, which video games want to do constantly. Graphics processing units that do all that heavy lifting are the perfect devices to perform this computation, what we call a correlation. And using those lets you do it cheaper and faster than ever before. Now, that's still not quite enough to pull this off, but it is enough to go halfway. Instead of having a full mirror, you can build a one-dimensional mirror and then use the computing along the other dimension. So you've sort of broken the problem in half. And we're now spending half our money on steel and half on computation. And this is a funny looking telescope. But it means that every detector on here sees a little band that runs from the south horizon to the north horizon. And then when you combine them all together, you can make them look in all these different directions. It's a weird operation. It means that we're doing some of the work in steel, some of it in silicon, but it does mean that we can build one of these ridiculously sensitive telescopes. And that's what we did. We built the Canadian Hydrogen Intensity Mapping Experiment, which is an experiment to map this hydrogen radio glow, the intensity of it, in Canada. This is what it looks like. It's a collaboration of 3 universities and Canada's Dominion Radio Astrophysical Observatory. These are large. They're 100 meters long and arranged north-south. We built 4 of them because that's sort of what you need to make the measurement. They're 20 meters wide. There are 1,000 detectors spread across these. And the end result is that you can actually make this measurement in a year or 2 instead of decades or centuries. Now, that's my background. That's where I was until, say, 2016. Meanwhile, in Australia, these strange signals were being picked up, these fast radio bursts. The first one was reported in 2007 by a series of astronomers and nicknamed the Loremer Burst after the first author. This is what the data looks like. This is a plot of time versus frequency, or if you prefer, radio color. And this black band is where there's more power coming in the radio. And at high frequencies, it comes in much, much, much earlier than low. Now, this is really weird. This particular slope is the thing that surprises people. This was actually something found in archival data. So this was data from 2001 taken on that Parkes telescope in Australia. And the weird thing, this slope is reasonably well understood. It's something called dispersion. It comes around because lower frequencies, so redder radio light, travels slightly slower through the interstellar medium, the plasma that exists out in the universe, just the few electrons spread around, than do the high frequencies. And that's something that's well understood. It's something that's been studied for decades in like pulsars, these rapidly spinning neutron stars. But if you just count up how much slope there is here, how much delay there is between the top and the bottom, it's way too much. This pulse seems to have traveled through so much plasma, through so many electrons, that it's from way beyond our galaxy. If you just add up how far away it is, you get into the sort of billions of light year distance. And that is a surprise. If it's astronomical, this was the only one seen at the time, remember, it means it's from billions of light years away, just from that slope. It's ridiculously bright to have arrived here so bright from that far away. And it's really fast. This is only a few milliseconds in duration, which means that it had to come from something really small, because you can't coordinate over large regions, these little pulses, just because the speed of light limits that sort of thing. So for years and years, it was not clear if these actually existed or if maybe it was just noise from electronics. This was seen at that Parkes radio telescope, and in the next few years, they observed a few more sources, but ones that were clearly from Earth and were eventually traced to their microwave oven. If you open a microwave too early, it lets out a burst of radio light, which happens to mimic this sort of thing. So for years, there was a debate over whether this was even real. Until in 2013, suddenly Parkes discovered 4 more of them, published 4 more, going through archival data. But that still was a concern because this is just one telescope in the world that seems to be able to detect these little blips that last, again, a millisecond and seem to come at random from unknown directions on the sky. Then in 2014, other observatories started seeing them. Both of those ones that I mentioned before, Arecibo and Greenbank, in their archival data, they started searching through it, and each discovered a fast radio burst. And that sort of convinced everyone that, oh, these things are actually real. Scientific American had a great description of it. This is in 2013, so before the others had come out, but they described it as a brilliant flash, then nothing. Fast radio bursts that mystify astronomers. And that describes them really well. They last for a millisecond, they're ridiculously bright, and then they don't do it again. If you miss it, you miss it. There were a lot of theories that came up for how you could do this. It takes a lot of energy to produce something this bright. So was it, merging neutron stars, exploding black holes, or newborn magnetars, or strange things like cosmic strings or axions? Are we looking at new physics here? No one is really sure at this stage. The trick is that if you look at how much data was searched and how many were found, these half dozen that had been found, it turns out that they're actually pretty common. They're, depending on how you model it, thousands all over the sky every day. So why is it that we could only find a few of them? There's a fairly simple reason, which is that if you use one of these big telescopes that's really sensitive, like Arecibo, it only sees something like a billionth of the sky at a time. It has a tiny little field of view. It's looking, it's got tunnel vision. It's looking at a tiny fraction of the sky, and the chances of catching one of these at random, it's just unlikely. If you use a tiny telescope, something like these old satellite dishes from the 90s, they see much more of the sky, but they're just not sensitive enough. They don't have a big enough dish collecting enough light. So radio dishes fundamentally are bad at searching. If you make them bigger to increase their sensitivity, they see a smaller region of the sky. If you make them smaller to see a larger region of the sky, they're not sensitive enough. So deep down, these are hard things to find. So you can take a step back and think, what we really need is a different sort of telescope that can look in a lot of different directions at once and be really sensitive and survey all the time. And meanwhile, colleagues and I had been building this for cosmological purpose. We did not come at this from the fast radio burst world. But our FRBs friends came along and talked to us, and we looked at it and said, yeah, we could probably repurpose Chime to do this. We could build a Chime FRB. And it turns out you don't even need to repurpose it. You can run both of these studies completely in parallel because it's all just stuffed in a computer. You upgrade the computer, you rewrite the software, and suddenly this is searching for fast radio bursts. And we did that. And the instant it came on, we started seeing them. By the start of 2019, we were showing up on the cover of Nature with the first series of results, described in Science as a homespun Canadian telescope, showing up in Wired, complaining that we looked nothing like a traditional radio telescope. New York Times broadcasting signals, IFL Science, that BBC article I mentioned, one from Nicole, talking about finding more and more and more of these events. And so much that in December, Scientific American came back and wrote another one saying that the science of fast radio bursts has come of age. And this is a beautiful graphic that they produced. Starting in 2001, they're showing pink dots wherever there's a fast radio burst detected. And you can see they're pretty rare. There are maybe a half dozen. We get up to maybe the dozen, 15 or 20. And then more telescopes from the rest of the world come online. And then here is when Chime turns on. And these blue dots are actually a huge underrepresentation of how many we've seen. Chime is now well over 1,000. And we're really just taking over the field using Canadian technology, which is great. There are some strange things about them. Some of these actually repeat. Most of them are one-offs. Some repeat. Some turn on and turn off. There seems to be a periodicity, a regularity to some of these turning on and turning off. And just last year, we suddenly had our first hopes that we might start to understand these. There was an incredibly bright burst last spring, which was traced to a magnetar, a super highly magnetized neutron star in our galaxy, only 30,000 light years away, which means we can study it in other wavebands. We understand this object better than these unknown things from other galaxies. This is the sort of source that's small enough, it's almost bright enough. It turns out it's not quite as much power as we see in most of these, but maybe we just didn't get the brightest one out there. So we're making huge strides with this enormous haul of detections that Chime is now getting, that Chime FRB is getting. We're now suddenly starting to explore these in greater detail and to understand them. So I'll stop there and we can switch over to chatting.
Perfect. Thanks so much for that. These things, Chime, definitely, when I saw the telescope, I looked at it and it's a half pipe, yes, the Wired story saying that you don't look quite like a normal telescope, but obviously it is doing an amazing job of detecting these. It's quite mind-blowing. The question is, why study them at all? I mean, what does this actually tell us about the universe?
Yeah, what are they, right? So part of this, I'm a cosmologist, so my bias always comes down to this is fundamental science. This is trying to understand the workings of reality and how it is that everything's put together. And one of the things about fundamental science is that it's hard to tie it directly to some innovation we'll have tomorrow. When people were studying electromagnetism in the 1800s, they did not imagine cell phones and streaming conferences or anything like that. But it's all necessary. From the fast radio burst standpoint, I think from an astronomical standpoint, it's kind of exciting that this is a new realm that's opened up. We couldn't even search radio data for this sort of stuff until computing power had reached a certain level, because there's so much data that comes off these things. Chime is a terabyte per second, it fills up a laptop hard drive every second of every day.
Wow.
All the time. And searching through years of that, it just wasn't possible until, well, the last couple of decades. And it's kind of amazing that as soon as we open up a new window on the universe, that we can look at this, say, high time resolution universe, rather than just taking a long exposure. What does it look like on shorter timescales? Suddenly, there are these crazy new phenomena popping up. It really is, it's indicative of how much more there is out there to learn about how things work. And if this is something from a magnetar, it tells us a lot about how physics can behave in these really weird environments. So magnetars, like I said, it's a highly magnetized neutron star, which is a complex sentence. But the magnetic field on that, it's something like 1,000,000 billion times stronger than the magnetic field on Earth. It's strong enough that it pulls apart atoms. It does crazy things to the matter there. And if this gives us a way to understand it, great. It may be that these can be used for, well, cosmology. My bias comes back into it. They're coming to us from billions of light years away. That provides us with a backlight to different parts of the universe, and a backlight that's impulsive. So it's just one pulse, and then we can study how that travels through everything on its way to us. So you can start to pick apart how structure evolved in the universe and how that plays into these other questions of, what is dark matter? What is dark energy? And are they something that we can eventually wrap our heads around and make use of?
Yeah. Now you talked about, catching it, it's bright, super bright, and then it's gone. But can we talk about the repeaters? Because this is a relatively new discovery, and discovered by Canadian as well. Let's talk a little bit more about them, because they seem pretty interesting.
Yeah, so the first, 5 or 6 fast radio bursts were just that. They were fast bursts, and they were what the Scientific American article described it as: a brilliant flash, then nothing. And then that first one out of Arecibo did it multiple times. It flashed and flashed and flashed, and then it stopped for a while. And then many months later, it flashed and flashed again. And that was a real surprise to everyone. First, that it was amazing that these were confirmed as real astronomical objects, and then that this was slightly different from the others. And now in Chime, we see both. We see one-offs and we see repeaters. And it may be that we're actually looking at different things. We still don't know if this is one class of objects or multiple. They do sort of qualitatively have slightly different features to them. And that's not really nailed down yet, but there is some thought in the community that there are at least 2 categories of things going on here.
Yeah, and it's so interesting because they're so recent. I mean, like you said, uncovered in 2007. Who knew? And who knows, I guess maybe there's another class or something like that you might have.
Exactly. Maybe it's 5 different things going on. And as we study them deeper and deeper and get more and more samples, we can start to tease these apart. That's why an experiment like Chime, where instead of getting 1 or 2 from the last decade, you get hundreds a year, really stands in a great position in the field. We're making huge strides in this. Sort of month by month, something amazing comes through my inbox, and it's really it's an exciting field to be in.
Yeah, for sure. And who saw this coming, right? That's the thing. Okay, so first I want to invite people to send in questions, because these things are pretty fascinating, and I'm sure you have many questions to ask. But I'm just going to put it out there, because I know the question anytime I write about it: are they truly astronomical, or is it aliens?
Yeah, is it aliens? Certainly early on, the first handful, there were a number of papers arguing this could be aliens for various reasons. Some people thought they saw a periodicity, that they only came every so often from different directions. That did not bear out. Some people have argued that this could be, aliens using light sails. So they are broadcasting huge amounts of power at their spaceships to accelerate them, and we're getting a little bit of spillover. And that's what we're seeing. That, to me, seems unlikely, because they would have to be spread all over the universe and have been doing this over billions of years. So it's tough for it to be aliens just because of the span of space and time that it seems to occupy. These have been going on for billions of years, and they, for all intents and purposes, will continue to go on for billions of years.
Yeah. What about, I mean, Chime is so unique, but are there other, like you're working on some other ones, I believe, like it's similar telescopes. Can you talk about that?
Sure. So there are a couple of extensions, actually. The first thing that's happening, Chime is great, but we can only tell where these are coming from to about a square arc minute. That's 1/60th of a degree on each side. So it's a small region of space. It's about the resolution of the human eye, right? We can see about an arc minute. But it turns out that if you look inside an arc minute at the distances that we can tell where these are, there are dozens or hundreds of galaxies that it could be coming from. We can't tell just from that. So one of the big extensions is that we're building tiny chimes, little single cylinders in different places around North America to tie in with the main one. And those will, along with Chime, let us pinpoint where these are coming from. And then we can see, what galaxy, where in the galaxy, how they're distributed over cosmic history, how they're distributed spatially much better. We'll be able to say a lot more about the origins of these with that. And then separately, Chime has been operating for a few years, and technology marches on. We thought we had an incredible piece of sort of miraculous engineering at the time, and we did. And it's still great, but the computational power in the last 5 years has blown up. We can do amazing things beyond what we could do then. And even just the communications technology, right? We're borrowing things from cell phones, and cell phones have changed a lot in 5 years. If you go and dig out your 5-year-old cell phone, you'll be disappointed. But so there's a lot that can be done. So there are a couple of new telescopes coming up. This one in South Africa, which is ultimately aims to be 1,000 small dishes, 5 or 6 meters, called Hyrax. And there's another one in Canada, which is going to be sitting next to CHORD, or next to Chime. It's called CHORD, Canadian Hydrogen Observatory and Radio Transient Detector, which is made up of hundreds of these small dishes again. And it's a little closer to that cartoon that I showed of just dropping detectors all over the ground and processing the whole thing. So as technology marches on, and as we understand, the science and the questions that we're asking better, we're coming out with bigger and better, fancier, more sensitive observatories. So CHORD, we hope, on paper, it's about an order of magnitude more sensitive. So that again can revolutionize our understanding.
So is Chime is it easily adaptable? Like, can you change the technology, like the components to it, so that it can become even more sensitive, or what you need to do?
Yeah, it depends on how invasive we want to be. If we want to change the color, the frequency band that it's looking at, that's pretty invasive. That gets to be a lot of work to upgrade it that way. It may happen someday, but immediately, no. If you want to add other science cases where we're just taking that same data and reprocessing it, that's a matter of writing new software. And that's something that we're doing constantly. There are now something like a dozen different experiments running on Chime, taking that same data and rechewing it in different ways. And that's really been I think the revolutionary thing about it, that having all of this work being done in computers means you can change what all of this work means. You can add on an FRB search. You can add on pulsar monitoring. You can add on mapping of galactic magnetic fields. You can add on dozens of new things. And that's the sort of thing that's let us adapt it. Chime was already well underway in its design and construction by the time FRBs were even shown to be real. So it wasn't being built for fast radio bursts, and now it's having a huge impact there.
Yeah, it's a good point. Can we talk about, because it was quite exciting when the source was traced back to a magnetar, and specifically in our galaxy. My question is, so are we going to see more of these in our own galaxy as opposed to in other galaxies?
Yeah, I think it's certainly a possibility. I think it would be reasonable to assume that, yes, there should be more either from this magnetar that we've already seen. Maybe it has another outburst. Maybe it doesn't. Or from others. There are other known magnetars in our galaxy. So I wouldn't be at all surprised if we start detecting other ones, from locally, from only tens of thousands of light years away instead of billions. Yeah, and from other nearby galaxies, when things are near, you can see fainter bursts. So it makes it a little bit easier. There are fewer things to do it, but there's a trade-off.
Yeah, yeah, for sure. What would happen if one of these were close to Earth? Not 10,000 light years, not 50,000. Let's say, a few light years away, or tens or 20.
Yeah, I genuinely don't know.
Yeah.
The amount of energy that these things put out, it's probably beamed, so there's some small thing coming at us. But if they're emitting it in every direction, if you just take the naive guess, they're putting out in a millisecond sort of what the sun does in a year. So it's a lot of energy dumped very fast. And if you had something nearby doing that, it would probably be noticeable. I imagine it would be minimally something like a serious solar storm, and probably a whole lot more than that.
Yeah. Not good, probably, is basically what we're saying. Not good.
Yeah. We're pretty confident there's nothing like that in our immediate neighborhood, though.
Yes. Yes. People are always worried about that, though. You always talk about the end of the world and in the astronomical sense. So, okay, so we have these telescopes out there. We have Chime, which is an amazing Canadian invention, homegrown. Well, here, this question is, so what about us? What about ordinary citizens? What can we do to contribute to this?
Yeah, so Chime has actually recently, or Chime FRB has recently started engaging with the Zooniverse, which gets into citizen science. So like I said, we're producing an incredible amount of data, and we have software that sifts it down hugely. But it's still really hard to tell a real one from, say, a microwave, a microwave oven.
Yes, yes.
And just to automate all possible detections is really tricky. So we've started delivering these to partners working on this Zooniverse platform, where just you can sign up. You don't even need to sign up. You can go and start looking at our data and classifying, this is real, this is not. It'll walk you through sort of what real ones look like, what phony ones look like. If it's just someone driving by with a cell phone and our software missed, that's easy for people to tell. And it's surprisingly difficult for software to tell still. So yeah, if you want to get engaged, look up Chime Zooniverse, like universe, but with zoo.
Yeah, the Zooniverse is great. It has so many other things that you can do there, but FRBs would be a fun one to do.
Yeah.
What about you? I mean, what is really fascinating about FRBs for you?
Some of it is just the sort of immediate gratification. The cosmology side, it's a longer term haul. That image that I showed from the South Pole Telescope, that's sort of a 6-month exposure. So you turn on the telescope and you stare and you stare and you stare and you stare and you move it around and you take pictures constantly for 6 months and you stack them all up, and then it takes years to analyze it and make sense of it. It's a slow and steady, workman-like effort to get out the cosmology. And Chime is going to take years to do its cosmology. FRBs, it was pretty thrilling. We turned it on, and before we even were officially commissioning the thing, events were falling off. Just while we were testing it, stuff was happening. And like I say, almost every week or every month, I get some amazing new thing in my inbox, which is neat to see. And our students get to work with the telescope, and every student has found FRBs at this stage. They get to sit there and watch things come in and characterize them. And there's an immediate gratification in the discovery. And it's fun just being in a new space where we don't even know quite what we're looking at.
Yeah.
It's very much the explorer in me that enjoys this side of it.
Yeah, I'm sure. It's really one of the wonderful things about I would say astronomy, cosmology, is that every time you think you have something figured out, or there's a new question, right? And you're learning new things. So that finally, I want to ask Mike, what I've been wondering. I mean, the whole time this FRBs have been going on, and then once we kind of nailed it down to magnetars, could it be coming from magnetars only, or could it be coming from other sources as well?
Yeah, that's the thing we're not sure of. Even the one that we saw from the magnetar was not bright enough to explain the FRBs that we see. It's a couple of orders of magnitude fainter. it's much, much, much brighter burst than we'd seen from a magnetar before. But it's not quite in the same class as FRBs that we see from other galaxies. So we think that that could just be down to magnetars putting out slightly brighter bursts, younger magnetars that put out more energetic things. But like I said, even if they do explain a portion of FRBs, it's far from clear if FRBs are one thing or multiple things. These repeaters maybe are different. There could be multiple classes within repeaters or within one-offs.
Yeah.
So there's a really good chance that this goes a lot deeper than we might immediately think.
Yeah, and I mean, really, you still have to understand the mechanism behind what's actually producing it, even if you know that it's coming from a magnetar itself.
Yeah, it's from a magnetar. But how well do we understand magnetars? Not well at all.
Yeah, exactly. Well, thank you so much. I really appreciate you answering some of the questions. I mean, we're going to have some more questions coming up soon from the audience, and now we'll turn it over to some questionable news.
That was fascinating. Thank you. And Keith, you've primed everybody with your showing that montage of headlines. So for those of you who have tuned in to some RCIScience events over the last little while, some questionable news is our attempt to try to have a little fun with fake news detection. So we're going to be showing you some headlines, and we want you to guess whether or not these headlines actually appeared in a real news outlet or if we have just made them up. Okay? Got it? Now, our two speakers, Nicole and Keith, are going to be playing along, but we hope all of you will play along as well. And just say real or fake in the comments, in the YouTube chat, or on Facebook Facebook comments. So please, let's see what you have to say. And we are going to start with, researchers created a magic carpet through light. Will this hoverboard make it to NASA? What do you think? Real or fake?
I can buy it. You can certainly use light to move stuff around. You can apply a force with it. So I wouldn't be too surprised if someone was trying to levitate something with light. Calling it a hoverboard feels like a stretch, but I'll take it.
Okay.
I'm with him.
You think so? Yeah?
Possibly.
Yeah. So you were talking about light sails earlier. That's kind of related to that, right? Okay. So yes, this is a real headline from the Science Times. The study was just 2 small mylar plates as wide as a pencil's diameter, and it was in a vacuum chamber. These were lifted by a series of LEDs, and scientists are hoping to use this model to study weather and climate, but the idea is, of course, in very, very early stages. And there's, of course, a lot of meteorological challenges to this. All right, let's try the next one. I actually really like this one. Earth is fighting a laser duel with the exploding Carina Nebula.
Yeah.
Is this real? Is it fake, or is it just real but with a really inventive headline writer?
I'm going to say it's real with a strange headline. It is yeah. People, I think they're maybe trying to push it, make it look more, I don't know, like Star Wars.
Yeah, I'm trying to think of what would be lasing in Carina that would come our way.
Well,
I might say no, just to mix it up. This is maybe made up.
Maybe not. Maybe this is made up. Okay, the answer is real, except that it's a really misleading headline. Yes.
Yeah.
Scientists are firing lasers from the Very Large Telescope. For those of you who don't know, astronomers are not that great at naming telescopes. The Very Large Telescope is indeed a very large telescope in the southern hemisphere. And this laser is simulating distant stars. This helps calibrate the telescope to look at objects like the Carina Nebula. I have a little problem, though. Doesn't duel imply that it's actually fighting back?
Right.
Yeah.
Yeah.
Exactly.
Yeah. All right. Well, hopefully that's not true. Okay.
Well, clearly we're winning.
No doubt. All right, next one. We have an extinction level interstellar asteroid is approaching Earth. Brace for impact. How many times have you read a headline like this? Nicole.
Too many times. So no.
No.
Oh,
Keith, what do you think?
I would have said I've read so many of these. Brace for impact seems a little optimistic.
Maybe, yeah. If you have an extinction level asteroid approaching you, probably bracing for impact isn't a great idea.
Not gonna help.
Okay, so
I'm gonna guess maybe yes.
you're gonna say yes? Okay.
Yeah, it's interesting because there are 2 things here. There could be an interstellar asteroid, but there's no impact. So I'm going to say no because it's the brace for impact part. But
Okay. Excellent. All right. Well, let's see what it's fake. That's right. Yep. I think that Celia or Carrie made this up. That's fantastic. Okay. This weekend's full snow moon. Hands up if you saw the snow moon. The full moon yesterday?
Yes, I did.
Okay,
Yes,
it was clear just enough. This weekend's full snow moon will split North America into and spark a lantern festival in Asia.
What?
Yep. What do you think? Real, fake? Or is there any truth to this at all?
I don't even know what would be meant by split.
Yes. What? And how is it going in Asia? What?
Yeah, that's
I don't know. I'm going to say fake. Just
okay. So I don't know. What do you think, Keith?
I'll guess real.
Real. So
this
is another example of a weird headline, but it is a real thing. Sunset and moonrise occurred close together on Friday night on the West Coast, but on the East Coast, they occurred together last night. So there was a full moon that was one night in one part of North America and on the other night in the other part of North America because of time zones and because of location. On the Earth where sunset happens in the moon's actual motion. So it's kind of complicated, but it also coincides with the end of Lunar New Year, sometimes called the Lantern Festival. So that people celebrate the Lunar New Year and with Lantern Festival. So I hope that anybody who was celebrating had a lovely evening last night. Okay, now we do have one final one. This was a contribution. The last entry. Okay. Astronomers find 5 dozen baby black holes in distant psychotic chaos galaxy.
That's okay. Again.
I think psychotic chaos galaxy would be the official name.
No, yeah. Real or fake? What do you think? Is this a real headline or was this us just really having fun one night?
I feel like there was something recently in the news about lots of black holes instead of one in a galaxy where they thought there was a supermassive. So I might say yes.
Yeah.
I'm going to say yes as well.
Real.
Yep. This is a real and very misleading headline that I would like to credit my friend Greg, who put this up on Facebook yesterday and said, where did they get this headline? And I said, we got to use that. So yeah, this is exactly what you were saying, a whole bunch of small black holes, but obviously the galaxy that they're in looks pretty weird. So I guess that's where the psychotic chaos comes from. But that is, is not a real galactic classification type. Thank you all for playing. Everybody who played along. We do this for fun, but also to let you know that sometimes headlines are not just misleading. Sometimes they're just plain wrong. So when you do get a weird headline perhaps in your social media feed, you might just want to check it out and make sure or stick with good news sources like Nicole, who is always a very strong writer, does her research and presents excellent stories on the CBC. Thanks very much.
Thank you. So now we have some questions from our viewers. And of course, let's start off with interesting something perhaps. Keith, this is an interesting question. So can the combined detection FRBs, the levels of FRBs, dispersions be utilized to make a map of the ionized concentrations of hydrogen similarly to the CMB image?
Yeah, that's an excellent question. So like I said, they act as backlights to the cosmos. These are going off. FRBs seem to be coming from billions of light years away. And that means that you can use them to measure how much stuff is between you and them. We're hopeful that we can make a map of how much ionized hydrogen there is, because that dispersion, that spreading of different colors so that the low frequencies of light come in later than the high ones, that tells you directly that you can read off how many electrons there are between you and the FRB. So if you have enough of them, you can, in theory, make a full 3D map of where all those electrons are, which tells you where the ionized hydrogen is. The downside here, the problem with that, is that it doesn't tell you where along the line of sight they are for any given one. And we think there could be some large clump of stuff right around the sources. We're not sure if of that dispersion, how much of it comes from our galaxy, how much of it comes from the host, how much of it comes from the space between. And it's the space between that we want. So the thinking is that with large numbers of these, we can actually make that measurement, but it's tougher than we had originally hoped.
It always is, isn't it?
Yeah.
So are there plans, this one comes in, are there plans to try to correlate fast radio burst data with data from gravitational wave astronomy to see if bursts might be caused by collisions between highly dense objects such as black holes?
Yeah, certainly there are. We've been talking with the people at LIGO and other observatories and trying to set up MOUs and sharing data so that we can search events. The tricky thing is Chime, we see a lot of the sky. We still only see about 0.5% of the sky at any given time. So the chances that we happen to catch one of these at the exact right moment, well, it's not 100%.
Yeah.
And as people probably know, these gravitational waves, it's really hard to say where exactly they came from. So associating the two isn't immediately trivial. Even if we do get an FRB and a gravitational wave goes off at a similar time, we know that the gravitational wave arrives immediately. It travels at the speed of light the whole way. And the light travels a little bit slower because of all that plasma. It travels at the speed of light, but the speed of light in a plasma. So making the association isn't immediately the simplest thing, but certainly there are efforts ongoing. There are discussions between the groups. So we're working on it.
Yeah, that's interesting. So I know we talked a little bit about other telescopes that might that are being worked on, but this question came in as well. Are there any plans for Chime to be expanded with more reflectors for greater resolution and/or sensitivity? So that's a good question.
Yeah. So that's one thing that I touched on earlier, that we are building these mini chimes across North America just for the greater resolution. Increasing the sensitivity, we'd really want to expand the main station substantially. And that's just kind of expensive, right?
Yeah.
It's a lot cheaper to add small ones at different locations. And you get a lot more bang for your buck that way. And a lot of Chime really has been optimizing bang for buck, because this is a Canadian effort, and we don't have the budget of our southern neighbors. We can't just throw budgets with bees in them.
Yeah.
at projects. So yeah, we're working on building these small chimes across North America that will tie in with the station for the resolution, so that we can tell where these come from.
Is there any interest in having maybe other countries come on board, kind of, like the Canada, France, Hawaii telescope, or something like that, where you can get other people involved that you can actually expand it?
The collaboration includes people from from the US and well, mostly just Canada and the US at this stage. It's a little bit harder because Chime just looks up. So if someone's in France, it's hard for them to see the same part of the sky because they're over here.
Yeah.
So there's sort of a natural scale that the collaboration grows to, that you can build these telescopes, which is roughly North America. It gets really hard to use telescopes in Asia or Europe. And you can't really use telescopes from, say, South Africa or Australia to help out with this.
So next question is, are the FRBs traced back to a magnetar or a magnetar plus pulsar type neutron star? If former, are the FRBs possibly released during the supernova? If it's the latter, sorry, why don't we record it repeating like pulsars?
Yeah, so magnetars are just highly magnetized neutron stars. Pulsars are also neutron stars, which are spinning rapidly and emitting from their magnetic poles. And so as they spin around, we see the light as it sort of sweeps across us like a lighthouse turning around, right? So you see these pulses of light from the pulsar. Magnetars typically don't have that sort of emission. Some of them do have detections in the radio. This seems to just be a magnetar, not a traditional. It doesn't have a traditional pulsar emission mechanism. So sorry, if the former, what was the?
If the former, are the FRBs possibly released during a supernova? If latter,
so this was a magnetar that we knew about previously. It's been a magnetar for a long time. And this seems to have just been an active period, an outburst of some sort. And it's thought that those are caused by, not my field of expertise, and not really nailed down. We don't understand magnetar emission fully. But it's thought that it's reconfiguration of the crust, so a star quake, releasing some amount of energy releasing material that gets caught up in the magnetic field and accelerated in strange ways, and putting out just a lot of energy.
So the next one, again, you did touch on this a little bit. Is there a version of Chime in the Southern Hemisphere? How is all the data that is gathered stored and made available to scientists? That's a good question, because that's a lot of data.
It's a lot of data. So there isn't an exact version of Chime in the Southern Hemisphere. The Australians have a telescope which they've reconfigured, which is cylinders. They have these cylindrical, one-dimensional telescopes called Upmost. I guess the telescope is Molonglo, but Upmost is the FRB searching experiment on it. They've instrumented a smaller region. They only look at they look at a smaller region of the sky with it, and have commensurately fewer detections. And it doesn't quite work the same way. So it's a little bit of a different beast, but Chime isn't unique in being a cylinder. Just after Chime was being built, some South African colleagues got together with us, and we started discussing this, and ultimately settled on that Hyrax project, which reuses a lot of Chime technology. A lot of the people involved in Chime are involved in that. So there will be, not cylinders, but something using a lot of the developments for Chime being built in the Southern Hemisphere. But there is no Chime 4 cylinders in the South.
Yeah. So now,
sorry, how is the data stored? That was
yes, that was a very good question. Yes.
It's a lot of data. Like I said, it's something like a terabyte a second that goes into our computers. And the sad answer is that the vast majority is not stored. We cannot afford to record it all. Basically, if you miss something, you miss it. So we have to do all of our processing live. We can record about a 30-second buffer of that data. And if we find something, then we try to freeze that and save it. But most of the data, if you can't process it, as we say, it falls on the floor. It just, the data runs off the telescope, and that's that. We try to process it into whatever form we think we can use it in. So for the cosmology, we integrate it. We just sum it up. We make it a long exposure, effectively. And we store snapshots every 10 or 20 seconds, depending on what exactly we're looking at. For the fast radio burst, we process it and feed it to the FRB search. And when something's found, we copy out as much data as we can. When nothing's found, we don't. So it's sort of the new reality of these radio telescopes, that since we can afford to process it, we've built much bigger systems than we ever had in the past. And now we cannot record all the data continuously. It would overwhelm us. And ultimately, we'd have to go back and process it anyway. So the thinking is, you have to process it eventually. Might as well do it when you start.
Wow. So do you think anything's being missed?
I'm sure things are being missed.
Wow.
There's no doubt in my mind that we are missing things constantly. I don't know what they are. If I did, I'd write a little algorithm to search for them.
Exactly.
That's sort of the cost of doing business. If and when we have ideas for what else we can look for, we can build that in and check. And we take occasional dumps of the entire array and just comb through it and try to understand it and make sure that we understand what's going on. But yeah, that's one of the honestly downsides of this sort of instrument, that you do have to leave some things on the table. It's all there for the next generation.
Wow. Well, it's interesting because it's almost like it's too good at doing its job. There's so much information coming in.
Yep.
Wow. Again, I want to invite people to send in their questions. Again, fast radio burst, really interesting, mysterious signals from space. It's the only time I like using mysterious in a headline, because they are really strange. So another question is, would there be any benefit to setting up a pair of your antenna at right angles, or set it up at greater distances from each other?
So setting them up at right angles, these are aligned north-south. If you set one up east-west, would that be useful? The reason that we put it north-south, we see this strip north to south, is that then when the sky rotates overhead, we get the entire northern hemisphere of the sky. Just as the Earth rotates, it naturally spins our telescope across everything. If you put it east-west, you get this narrow band east-west. You'd get a lot more time on each part of the sky, because you'd see it from rise to set, but you would not get as much of the sky. You just look at each portion more of the day. So is there an advantage? This is actually something that Australian Cylinder did. It's an old telescope. It was built in maybe the 70s, called the Southern Cross. It's a north-south, 1 mile long cylinder, and then an east-west mile-long cylinder built on top of it. And that's something that they did back in the day, because then you can combine the two and you can sort of steer around where it's looking if you're only making one beam, if you're looking in one direction. With Chime, we don't do that. We eat the cost and we look everywhere all the time. We have 1,024 of these different beams looking in different directions. So adding an east-west one wouldn't gain us a lot on Chime. For building ones a little bit farther away to increase the resolution, yeah, that's a great idea. That's something we're working on.
Oh, wow. So now for the original Chime purpose, has the red-shifted 21 centimeter emission signal from the reionization era been detected?
So the reionization era it's an early period in the universe's history. When the universe started, it was all a hot, dense plasma, and then it expanded and cooled off. The CMB came out, and then it was just dark and boring for maybe 500 million years. And eventually these structures formed large enough that galaxies were born and stars started to light up. And when that happened, it ionized the universe. All of the energy that was given off by these first stars or first galaxies coming together it let off a lot of, the entire process isn't fully understood, but it reionized all of the hydrogen. So it knocked all the electrons off. That happened very early on. And that's something that people have been looking for in radio for a long time, because it should be obvious in theory. Before it, all the hydrogen is neutral. So all of this 21 centimeter, this radio glow, everything is glowing that way. And then the universe ionizes and everything stops glowing to first order. So you should see just this step. And people have been looking for that since about the 90s with other radio telescopes. Chime can't actually see that. It's looking at a different band of radio light. It's looking at a different portion of the radio spectrum. We're at higher frequencies than you would need to see that. So there are a number of other telescopes, primarily in Australia and in South Africa, that are looking for this. And as yet, it has not been detected. At least it's not published in any way.
Not yet. Well, still something to look forward to.
There is one publication from a small telescope in Australia that saw what they call the global step, which is the very, very start of reionization. And I think that hasn't been reproduced yet, and it's not, the world isn't yet convinced that it's real. But I guess that's the caveat to my statement. It may have been seen. The larger telescopes that are looking for it have not yet seen it.
Yeah, that's too bad. So, okay, you mentioned Canada having less of a budget for instruments compared to the US. Can you tell us about any other thrifty Canadian astronomical experiments?
Yeah. So like I said, Chime had to be done on a budget. Everything we do, we try to save every possible penny on. We're kind of cheap about the whole thing. There are others. A really good example, I think, is the Dragonfly array. This is a series of cameras connected to professional, but lenses. So things that, say, paparazzi would use to get telephoto images of things, large, sensitive to low light lenses from Canon. Those have been, put together into an array with a lot of cameras stuck on the back and used by colleagues here in Toronto and also their collaborators in Yale to look for, ultra faint galaxies. So they're looking for very, very, very low levels of light. So galaxies that don't have many stars doing anything in them. And they've made some amazing discoveries. And that, again, is on a tremendous budget. And a lot of it comes down to what can we repurpose from the rest of the world? Astronomers, we can't really drive industries forward, but we can look around and see, cell phones, video games, cameras, these are things that exist now. And we can repurpose them in slightly non-traditional ways to make really good, innovative measurements. So Dragonfly, one of the things that they found was they found galaxies that are almost entirely made of dark matter, it seems, and kind of a mystery. There are great things coming out of that world too. Yeah. So if we can find these neat little niches that they're a space that we haven't been able to study for before. In the case of Chime, it's a lot of this sort of stochastic radio events, so things that happen unpredictably and things that are fast generally in radio. It's a new space that we can explore. And in the case of Dragonfly, looking for these really, really faint surface brightness things, just galaxies that are really hard to see because they're not putting out much light.
If you can refresh my memory, who university in Toronto who's running that? Or
Bob Abraham is leading that.
Sorry?
Bob Abraham?
That's it. That's great. Yeah. Well, it's exciting. And I mean, that's the thing, I suppose, in in the astronomical field, you just sit back and wait for some great technology for cameras, phones, and you like, how can we use this?
Yeah, I wish we could sit back and wait, but
yeah, I know. So another question is, do you work with other teams studying FRBs across Canada and internationally? And if so, what has the experience been like?
Yeah, the FRB world is pretty collaborative. It's been really nice. So, for example, that repeater, the first FRB that Chime found that was a repeater, one of the early ones that we found, we worked with a team in Europe to localize it, to figure out what galaxy it's in. Because again, Chime can narrow down where it is, but there's still dozens to hundreds of galaxies in the region that we see. So we worked with a team primarily out of Astron in the Netherlands to use telescopes, more traditional radio telescopes spread across the Earth to detect future bursts and figure out exactly where that object is. And in the case of, say, the magnetar, when we detected it, it was actually way outside Chime's main field of view. We just were searching, and we caught it out of the corner of our eye. But it was so bright that it lit up, I think it was 93 of our 1,000 pixels that we see. So it was bright enough that it sort of splashed across the whole sky. And we saw it, and we put out a little notice, and we noticed that it was coming from the magnetar, and that was exciting. They don't usually have this sort of burst. And there was a US team that took that and went and looked it up and found, goodness, this thing is really bright. And we sort of, talked to them and put out papers simultaneously describing the event. And a lot of these things, depend on other communities. In that case, we also worked with X-ray groups that are operating X-ray telescopes to see that there was an X-ray flare from the magnetar at the same time and looked to be associated. And that helped really nail down where it was coming from. So yeah, we try to collaborate as much as possible with as many groups as possible, because honestly, more heads are better than fewer. These things are often complicated, and having a lot of eyes on the problem is a good thing.
Yeah. I mean, in this field in general, in cosmology, astronomy, all that, it seems to be a very collaborative field. I mean, it's a big universe.
There's a race. We're competitive. We're trying to get these things before everyone else does. But that said, we know that we're all on the same side.
Yeah. So question, has SETI expressed any interest, so the SETI Institute, have they expressed any interest in searches going through your data for intelligence signals, going back to the whole alien idea?
Yeah, there have been a few discussions back and forth with that. Nothing is sort of formalized yet, but we have discussed what that would look like and how that could be done.
That's really interesting, yeah.
Yeah, it could be interesting. SETI searches are pretty expensive because that's you don't know what the signal you're looking for is. And typically the thing that they look for, things like really, really, really narrow band emission that doesn't get produced naturally. Yeah. It's computationally expensive to do that. And getting through all our data that way, it would be a significant upgrade and rework of a lot of the computing. So yeah, we're having discussions. We're looking at building that into some of the future ones from the get-go. And yeah, I think it's a worthwhile thing to search for in parallel with all these others. Since these are these funny digital telescopes where it's all, you can clone data and it's not doing A or B. It's doing A and B, and C and D and E. Doing all of these projects at once. It makes sense to try and get these value add things, even if you think or I think a priori low probability of finding something. I think it's a worthwhile effort because high reward.
Yeah, exactly. That would be. So now, a question: are these small, innovative experiments the way of the future, or is it large installations like ALMA, or could this be a combination of both?
That's a great question. I think it has to be both. There's so many things that ALMA or the next generation radio telescope, the square kilometer array that's proposed, these huge observatories can do other things that these smaller, what are sometimes referred to as boutique experiments, can do. The boutique ones are sort of smash and grab. We can put together some quick test, some high risk, high reward thing on a limited budget and put it out there and check, and hopefully make huge advances. But once people are, these big observatories, they can do things that we just can't do. Like Chime is fixed on the ground. It's bolted to the ground. We cannot steer it. We can't follow objects. We can't take long integration. We can't sort of look at them for a long time and see what they do. And that's a necessary trade-off in the design. Making the thing steerable would have made it hundreds of times more expensive. But that means that it's blind to a lot of things. So I think you really do ultimately need both of these. I mean, even for Chime's studies, when we localized that repeater, that depends on these huge telescopes, the Arecibo and Effelsberg, 100-meter dish in Germany, and the Green Bank 100-meter dish were used for that. So you need these big facilities, even just to do the things that I've been talking about. And X-ray telescopes; those are hundreds of $1 million sort of jobs. So it takes both, even if you're only interested in the stuff that Chime can do, and to do all of the stuff beyond what Chime can do. Observatories are they're a critical piece of this. Having these big international efforts, I think it helps a lot, and it pushes a lot of envelopes in technology development, in the science generally. It makes people think of what you can do with some giant telescope. Meanwhile, you can take a smaller budget, you can put something together quickly with some grad students and half a dozen faculty from across the country, and you can do amazing things.
Yeah. Would there be any interest, or would there be any benefit really to sending a telescope into space that could look for FRBs?
Yeah, the one place that I think might be really nice is a dark side of the moon telescope. That's been my dream for as long as I've been doing radio astronomy, because on Earth there's just so much junk. People make so much noise. It's true in visible light. We have all of these street lights. We have City Glow and Starlink things now overhead, and no end of light producing objects. And you just get a clearer picture when you get above all that. And in radio, it's honestly a lot worse. There are blindingly bright things all over the planet, from cell phone transmitters to cell phones, to radio towers, to airplanes, to every satellite that goes overhead. And all of those are easy to confuse for these sudden blips, because they also make sudden blips. So for example, that Green Bank fast radio burst, the second or third telescope to discover an FRB, they had an automated system to go through and search, and they still had to have a student go through, I think it was 6,000 candidates to see if any of them were real. And you can only imagine how that student felt after 5,000 false ones before finding the real one. So yeah, I think getting above the RFI and getting something between us and the Earth, like say the moon, would be great. But now, of course, people are landing on the dark side of the moon, and there'll be all sorts of radio towers there before we know it.
No, I hopefully not, because I know there has been a lot of talk about using the dark side of the moon for that purpose, for different experimentation, like very, very different searches. That would be something else. And what could you mentioned starquakes? What are some of the leading theories as to what could be possibly producing these FRBs, if it is indeed on a magnetar?
This gets way beyond my expertise. I'm not sure that I should venture an explanation.
Well, just anything that's out there, like if, so starquakes, is there anything else?
Yeah, I mean, ultimately, the energy comes from the magnetic field. These things have huge magnetic fields, and it's transferring some energy from that into a radio emission. And the basic model that I've seen is that for some reason, some material gets kicked up from the surface into where the magnetic field is, rotating quickly, and strange things are happening there or not. And it gets really stirred up and superheated by that magnetic field. And then it just emits in these small clumps of gas, fire out some emission, which can be anything from X-ray down to radio. And it may be continuous or clumpy across the whole range. And yeah, that's honestly as far as I've got into the explanation, because I think it's such an exotic state of matter. I mean, neutron stars alone are something that we have a really hard time understanding and explaining the physics of. So neutron stars with crazy magnetic fields embedded in them, it's at the edge of astrophysics. It's not something we understand well, and why they would be producing these things, I think, is going to help explain that rather than the other way around.
Neutron, and it's such a new field. I mean, like, we just found them in 2007. Well, then we found repeaters just after that, and then we're just, now we finally found one locally. So I guess it's all just evolving, really, and it's evolving very fast. Actually, great segue there. Speaking of fast, have there been any collaborations with the Chinese Fast Tianyan Radio Telescope group?
Right. So the FAST telescope, for people who don't know, it's like Arecibo in the sense that it's a giant fixed bowl of a dish. But Arecibo is 300 meters wide. FAST is 500 meters wide. It's half a kilometer across. It is the largest radio telescope by a lot now, and accordingly the most sensitive. They have a hard time doing searches because they, again, see a billionth of the sky at any given time. But yes, there have been some collaborations. I believe they looked at the magnetar and confirmed a radio emission just after. So this isn't direct collaboration, but it's sort of trading off. It's the way science typically works, that we put out something, someone else looks at it and then upgrades it, and then someone else upgrades that, and you build off each other's work. So yeah, after the original burst had been sort of mentioned, they steered FAST over and took a look at it. They do it like Arecibo. They steer the reflector and they distort the dish a little bit. They don't move the whole bowl. So that they were able to look at it and confirmed that more bursts came out. They were fainter than the one that we caught, but because they're so sensitive, they could see much fainter bursts. So yeah, FAST is another sort of mega facility, which is amazing and can do incredible things that Chime can't quite do.
Yeah. But it's great to have a new telescope, again, that can look at it differently. And now the final question comes in, and it says, when will the Chime team get their Nobel Prize?
I am not making bets on that. I'm going to stay away from that. I think it's probably left to the experts.
It is quite the achievement, though, and it's definitely something I think that we can be very proud of in Canada. And it's going to be so exciting. When I first, recorded, like I first did my interview with one of the Chime collaborators, one of the scientists, they're like, yeah, we went from detecting a few of these to the possibility of detecting hundreds of these in a week or whatever. That's just amazing. So, yeah. So congratulations to you and your team. And now I'm going to hand it back over to the group. I think it's Chris.
Afternoon, everybody. Afternoon, everyone. And my name's Tom Luton. I'm the president of the Royal Astronomical Society of Canada, and I'm going to be taking this opportunity, first of all, to thank you, our partners at RCI, for this wonderful lecture, and going to give a brief talk a little bit about our organization and who we are and what we do. So to move on here. So with a name like the Royal Astronomical Society of Canada, you'd think that we were the professionals. But the interesting thing is we are actually the largest amateur astronomy society in Canada. We're founded in 1868, and there are 30 centers spread across the entire country. Toronto Center, of which I'm the president of, was the first center, and we're located in the normal times at the Ontario Science Center, where we host speakers, we have star parties, and we have meetings by our members that are held for free for the public. We welcome everyone to attend. We also help operate the David Dunlop Observatory in Richmond Hill with speakers and star parties and other events around the GTA. Now, you'll notice that I said during good times. The COVID outbreak has, of course, forced us to move entirely online. Just going to give you a brief introduction to what we've got coming up. We have our recreational astronomy night coming up on the 3rd of March. We have our speakers night coming up on the 17th of March, and we've also got some upcoming online star parties. All of these events are viewable for free on YouTube. We also have DDO talks coming up online. You can register that are for free. You'll have to register for those. We've got DDO Astronomy Night on March the 6th. We've got DDO Up in the Sky on March the 27th. And we have DDO Ask an Astronomer on March the 28th. Again, all for free. You'll just have to register. So please give us a visit at rascto.ca, which has our complete list of programming and our schedule for coming up for the coming weeks. And we'd love to see you there. And when things get a little more normal, we'd love to see you back at the Ontario Science Centre. So thank you very much, ladies and gentlemen.
Thanks, Tom. And thank you also to our speakers, Keith Vanderland and Nicole Mortellaro. That was a fascinating discussion. I really enjoyed learning more about Chime. I'd heard quite a lot about it, but you really gave us a great insight into, again, how thrifty Canada can be. I think that's great. We also hope that all of you enjoyed today's discussion, but we would like to hear your feedback if you can. We will distribute a link to sign up to, or to, it's a link to a survey, pardon me, that will allow you to give some feedback on our program today. We do hope that you will tell us what you thought and also give us some idea for future events. If you can, we would also like you to consider supporting RCIScience's free programming like the RASC. We've also been online since last March or thereabouts, and this does still cost money, so we would really enjoy if you could support us, rciscience.ca/donate. We have a lot of interesting programs coming up. You heard about the ones at the RASC. The RCI Science programs in March are going to focus on, guess what? COVID-19 vaccines and the pandemic. So we're going to be playing an online trivia game, Quarren Trivia, which we actually had an opportunity to play back in the fall. That was actually a game developed by a student at the University of Waterloo. It's a fascinating game. And also, there's going to be a panel discussion on the COVID vaccines led by Science Sam. That's Samantha Yamin. Should be fascinating, very timely, very interesting, and very important. RCIScience.ca, what's on, is where you can find out all about what is coming up here. Also, please follow us along on social media, on Twitter and on Instagram. And on Instagram in particular, we have a lot of scientists taking over our Instagram account and using it to talk about their research. Fascinating stuff, including a research-informed look at vaccine hesitancy. So I would like to close by thanking everybody for joining us today. It's not a very nice afternoon here in Toronto, so I hope that you've enjoyed spending your afternoon with us. And for all of those who joined us from farther away, that's amazing. I love to see that. Welcome, and I hope that you'll join RCI Science or the RSC at a future event. Thank you. Have a good afternoon.